Hello and welcome back to another video in this series as we learn the basics of Lean to write simple maths proofs. Today's really exciting, I think, because we are going to be looking at a very different type of proof, and the type of proof is called an existence proof, proving something exists. We'll be looking at simple maths examples as usual, but the nature of the proof is very different to anything we've done before. We're not kind of calculating a result, we're proving something exists, but let's have a look and dive in. So the aim of an existence proof is simply to show something exists, not necessarily to justify where it came from, and that's kind of important, and it sometimes makes it easier as well, as we'll see. Now, it may be subject to some constraints, but we'll see that as well. So let's look at a simple task, an example. So the question, the problem is, show there exists, and that's always the key phrase, there exists, show there exists a natural number n such that, so that's the condition, such that n squared plus 1 is 10. So we're not working out whether n is 5 or n is 2 using some kind of substitution and the usual thing that we do. We're not doing that kind of calculation. What we're asked to do is to say, yep, there's lots and lots of natural numbers, an infinitude of them. Is there one that meets this condition? And what we have to do is show that there is one by showing that it meets that condition. We don't have to justify how we found it. Sometimes how you find it is interesting and sometimes it's not. Now, if I gave this to you person to person without pen and paper, you could probably do this in your head. You could say, let's see, well, n squared is always positive, plus 1 increases the sum a little bit, and it's 10, so n can't really be a big number, can't be 20 or 100 or 1,000 or a million, it's got to be quite small. So 1, too small, 1 squared plus 1 is 2, 5 squared is 25 plus 1, 26, that's too big, so it's somewhere between 1 and 5, so that's not too difficult to search. Let's say 3 squared is 9 plus 1 is 10, so we found n. We found that n is 3 satisfies this condition, and that's all we need to do, in terms of proving that there exists a natural number n such that n squared plus 1 is 10. Now, there's some mathematical notation that goes with there exists, that phrase, and it's this backwards e symbol, there exists, and you might see it written down in mathematical kind of notation. So there exists n from the set of natural numbers such that n squared plus 1 is 10. You might see it in different forms. You might have round brackets, you might have colons, you might have other things, but broadly that's kind of, you should recognize it when you see it. Sadly, there isn't a universal convention for these kinds of statements. I wish there was, but people seem to have their own kind of house style, I guess. Right, so the slides are online if you want to download them and read them more slowly. They're just kind of repeating what we've said if you want to read it at your own pace. So remember what we just did. We kind of did a guessing game, trial and error, and we found n is 3. So calculating or deriving or even guessing, that's not the central point. The central point is finding one by hook or by crook, by whatever means, and then showing that it meets any conditions that are relevant. So we found n is 3 and it satisfied that condition. We don't need to justify how we arrived at our example. That's important. So let's see if we can write this down as a proof that gets us ready for translating it into Lean. It's not long, so you can probably see that the Lean proof won't be that long either. So we write the proof objective at the top. There exists an n, which is a natural number, such that n squared plus 1 is 10. Now remember, we don't have to justify how we found our example. We just have to have one that we think works. We propose one. So we are going to propose n is 3. So we say use n is 3, and that's our chosen example. Now if n is 3, then this condition becomes 3 squared plus 1 is 10. So we've shown that n squared plus 1 is 10, that the condition holds when n is 3. And that's all we need to do. So there's two parts to these things. One, finding the example, and we don't have to justify how we do that. And part two, showing that any relevant conditions are met. And that's the bit that's the meat of the proof. So you can see here the meat of the proof is showing that the conditions met, but by some magic we found n is 3. But as I said earlier, the onus of a proof, existence proof, is not how you found that, but once you found it, that's sufficient as long as it meets the conditions. So let's see what this looks like in lean code. So in lean code, you can see there's some new things here. There's a couple of new things. So we've got, we normally have a declaration of variables, and then we sometimes have hypotheses before the colon. So they have the curly brackets and the round brackets. There's nothing here. So we've not declared variables up front. There's no hypotheses. All we have is a proof objective, which encodes the fact that n is an integer. So the proof objective says there exists an n natural number, such that n squared plus 1 is 10. And we need to provide an example, remember, and we're going to use the instruction use. So use 3. That will transform the goal, which we'll see in the Infoview in a minute, from n squared plus 1 is 10 to 3 squared plus 1 is 10. So we're going to do that by calculation. We're going to say 3 squared plus 1, and we have to prove that's 10, and that's easy by arithmetic, so it's kind of almost trivial. So this is a very easy calc section. We'll see that we can actually shorten it in a minute. So let's look at the Infoview a little bit here, because there's a lot going on behind the scenes. This code is really short, but it can be deceptively short. So again, you can download all the code from GitHub, and you can run it in Visual Studio Code, or you can run it online with the online lean environment, so you don't have to install anything. And the links from the blog. So we have the proof header. Remember, there's no variables, no hypotheses, just the proof objective. And it's saying that n is a natural number, and such that n squared plus 1 is 10. So there exists a natural number n, such that n squared plus 1 is 10. And we are going to say we think 3 is that example that proves that there exists that n. So before use 3 is executed, let's have a look at what lean thinks. So there's no hypotheses. See over here on the right? There's no hypotheses, there's no declared variables, only a proof objective, which encapsulates all of that. The proof objective, there exists an n, such that n squared plus 1 is 10. After use 3 is run, that becomes that the proof objective changes and the n's become a 3. So we now have to prove that 3 squared plus 1 is 10. So it's almost substituted. So let's step back and talk in plain English. We wanted to find an n such that n squared plus 1 is 10. We think it's 3. So we have to prove that 3 squared plus 1 is 10. It really is as simple as that. So that's why that proof objective has changed. And then we just use a simple calc section to prove it using arithmetic. So this should be quite familiar. Now you might see here a second version of that, which is shorter. And up to this point, after use 3, the proof objective is 3 squared plus 1 is 10. And because that's so simple and can be done almost in one line by one tactic, you can just apply the tactic. So that is more concise, smaller code, but you should really only do this kind of shortening if it is really simple and absolutely clear to the reader what's going on. There's no point having super brief code if no one else can understand it, and if you yourself come back to it later and can't understand it. So this, it's really clear what's going on here. It's longer, but we know what we're doing here. This, if you're familiar, you know what's going on. If you're very new, you might not. But I think over time, very simple objectives like this, we'll be happy to say, yep, we can just use norm num, and that resolves the kind of the objectives there, because it's simple enough and there's no confusion to be had. So that's a kind of a more concise version, and you can practice doing that in the exercise at the end. So let's just draw a picture, because we haven't done one today. So let's say, let's kind of pick an artificial example. Let's say the proof objective is there exists an n, which is a natural number, such that, or n is more than 10. Now remember, we just have to find an example that satisfies this, and it doesn't matter how you do it. So what could we do here? Well, we could choose n equals 11. We could try that. Does that satisfy the constraint? I remember there might be lots of constraints, but in these simple examples there's just one. Yes, it does. So that's, we've proven there exists an n natural number such that n is more than 10 with this example. But we could have chosen n equals 12, or n equals 1002, or any other number larger than 10. So there are sometimes lots of options and possibilities, sometimes an infinity of them. So I just wanted to kind of show that in case you came across it later and you thought, oh my god, is that right? Is that wrong? It's perfectly fine. I'm not going to let you go just yet. I think it's worth looking at what happens if we use a bad example. So with our one, if we chose n equals 5, and that was a bad example, warning, it doesn't meet this constraint. So if we try to substitute that, we want to prove n is more than 10, and if we're saying n is 5, we're trying to prove that 5 is more than 10, which we just can't do. We're never going to prove that, so that will always fail. So let's see what that looks like in live lean code. So we'll use our example that n squared plus 1 is 10. If we say 4 instead of 3, so if we think the answer is 4, if we think 4 is a good example, that means 4 squared plus 1 should be 10. 4 squared plus 1 is 16 plus 1 is 17. 17 equals 10. That's not right, is it? So if I use 4, what happens to the proof objective? 4 squared plus 1 is 10. And we're never going to, no matter how good we are at coding, we're never going to prove that. No calc section is going to prove that 17 equals 10. So that's never going to work. So you'll get an error. You'll get warnings and kind of red underlines to say that didn't work. So that's there. Let's see what happens with the shorter version. Yeah, there's a warning there, but the right hand side will say unsolved goal. That didn't work. Put 3 and it's all gone away. No goals, all messages 0. Fantastic. So sometimes it's worth seeing what happens if you deliberately get things wrong, because when you're writing more interesting proofs, you will get things wrong, and it's worth having seen some of those errors before, especially when you know that you've constructed them deliberately, so you can see where they came from. Great, so that's just a slide on writing it in a shorter way. We've talked about that. And the easy exercise is again very similar to the example we have. And the idea is to prove that there exists a natural number. Well, there it is. Prove there exists a natural number greater than 5. So prove there's an n, which is a subset, which is in an element of the set of natural numbers, such that n is more than 5. And actually we kind of showed you how to do that. You can pick 6, 7, 8, 9, 10, a million. But so the proof shouldn't be difficult, but have a go. And in this one, it should be simple enough for you to try writing the concise form as well. So have a go at that. Any problems, come back in the comments and we'll have a chat about it. So that was exciting, something very new today, existence proofs. I think that was a nice one to kind of do. We've come quite far actually from the very beginning, where we were just looking at substitutions, and now we're looking at more interesting things like existence proofs. So congratulations if you made it this far, and we're going to keep going. So we'll see you next time. Bye.